let's talk about what a vector really is. And a vector is a quantity that has a magnitude or an amount or a length and a direction. Now, the opposite or the counterpart to a vector is a scalar, and a scalar only has the magnitude or the amount. We don't care what direction a scalar is going to be in. Examples of scalars are things like time, temperature, mass. So there are several different ways that we can write vectors, but we're going to talk about two useful ways. And that first way is to use component form. And for component form, I have my generic vector v, and your book talks about how it will write vectors using boldface, but that's difficult to do when one is writing by hand, so I usually put that arrow on top. And the components of vector v are, I'm going to use this hard bracket here, and I'm going to have an x component vx, comma, a y component vy. And if I were to draw this vector, so here's my vector v, and let's say that it will be on some coordinate system, then I drop down a line this way, and this is going to be my y component, and this is going to be my x component. Now, another useful way to write vectors is to write them in terms of their magnitude and direction. My generic vector v here has a length of the absolute value of v. That's how we denote the magnitude of the vector, and this is going to be equal to the square root of the sum of the squares of the components. So it's going to be the square root of vx squared plus vy squared. And if you go back to our triangle up here, you can see using the Pythagorean theorem that the length of my vector v is going to be the square root of this leg of the triangle squared plus this leg of the triangle squared. And that gives us the magnitude, but the direction is going to be this angle theta here, which we measure with respect to the positive x-axis. Now, one final thought is, as the book says, a vector can be moved anywhere and still be the same vector as long as the length, or the magnitude, and the orientation, or the direction, stay the same.